Anyway, why don't we start with the multiple choice question answer creative? It's essentially asking, given that A star search is a special case of malcodation processes, we'll be talking about this a lot. What corresponds to the value function in MDP to something in A star search? Okay, and I gave you three answers there: F or G or H values. Pick which one it is. I'm going to start with multiple choice questions.
Excuse me.
If everybody gets a chance to weigh in. Okay, we have 6:59 or 61 people. I'm going to essentially stop soon if you want to wait. This is an MCQ, so this is just to try and see where people are. The next one is more important. I'll leave it on for a longer time in the class by the continue. That's the attendance. I know people are complaining that. I mean, they're typing away, texting away during the class, but somehow they can't get on to concentrate time. But we leave this one in the background as they continue so that you have a long time to put your. Okay, so I'm going to start the first question. Let me just show you how it looks. Okay, so that's how it looks, right? So the way I remember asking, so basically A was F value, B is G value, C is H value. Okay, so somebody who thought it was, let's say, D, which is G value. Why did they think so? There were people, so 19% of the people. Somebody who thought it is C, which is H value. Why did they think so? Yes? What's your name?
I'm Jackson.
Okay.
I put C because I thought that.
Speak louder.
I put C because isn't the H value the associated value function for the A star search?
I can't hear what you're saying. H value is the?
I can't talk any louder, I'm sorry.
Really? I never had that problem. So H value is, what are you saying?
Isn't the H value the value returned by the function? The value function assigned to the A star search?
Yeah, but I don't know. I mean, I guess, I'm not sure. That you're saying isn't H value the value assigned by the A star search? That's not a good enough reason as to why it should be value. Anybody else who said it is H? Would like to weigh in? Yes, what's your name?
Riley,
Okay.
is the H value and the value function both like corresponds, like how much is like left till the goal state?
Do you guys get that, what he said? Value is not about past, it's about future. Okay? The value of a state is not about how much fun you had blundering into this state. It is about how much fun you're going to have from this state onwards if you do the optimal action. Okay? So the value is cumulative reward you expect to get, or it can also be thought of as cost to go. Okay? Which is why it's very important to understand that in fact value function corresponds to the H function in A star search. Which also should make you wonder if you in fact wind up taking some A star search problem and write it down as MDP problem, which you can do especially if you use the cost oriented model, which we'll talk about a little later. Then when the value iteration converges, what would the optimal value function be like? What would be the optimal value function corresponding to the A star search? We already said value function is heuristic. So the optimal value function should be what? H star. Okay, this sort of stuff makes people understand. I don't know that it makes you understand, but it should make, I mean, the whole point of life is to connect everything that you know, so that the way I think about it is small things can then easily drop through the cracks of your brain, and there are huge numbers of cracks in your brain. Okay, so if on the other hand you connect everything, hopefully all of it doesn't fall down. Okay, so A star search is connected to MDP. You see, and in fact, value function is essentially computing the heuristic value, and when you actually compute the optimal value function, you are essentially computing the perfect heuristic. And that makes things so much interesting. You should feel really happy about it. If you are not, then there's something wrong with you. You should improve your reward. Yes?
But for MDP, we also calculate like the reward of the current state. So isn't that kind of like the G of that as well?
No, the G is the cost to reach the state from wherever you are starting from. In fact, there is no notion of G in MDP because there is no given initial state in MDP. You see what I'm saying?
That makes
A
sense.
star search has a given initial state and it reaches a particular goal state, whereas MDP is essentially wherever you are, try to have lots of fun. That's what the MDPs are saying. And so it really is H value connection. Yes, sir.
So does this mean that not every A-star search problem can be translated into an MDP problem?
Well, all it basically means is that if you write MDP in a cost-oriented way instead of a reward-oriented way, we'll talk about it in a minute, actually later on in the class. We've been looking at, there are like many different ways of formulating MDPs, syntactically speaking, and in fact, I will actually show you that because the MDP homework questions expect a formulation that's slightly different from the textbook formulation. Okay, and so I'm going to talk about this today. And in that same slide, I'll also talk about the cost-oriented formulation of MDP. And if you do the cost-oriented formulation of MDP, that's basically can be seen as what they call stochastic shortest path algorithms. MDP, A star is shortest path algorithms, right? And if you do a cost-oriented version of MDP, it will become stochastic shortest path MDP. MDP is, within that same framework, you can put many different variations. We're just talking about one variation by default in the foreground, but there are all these other things you should be able to get easily used to. Yes. Yes.
Yeah, so in the last class we discussed cost as a negative reward. So,
Yeah.
So in this case, in A star, shouldn't we consider the past cost as a negative reward to a particular?
No. Cost is, basically, the idea is you can think of everything in terms of rewards or you can think of everything in terms of cost. But either which way, you can have some idea of value function for MDP. And the value function would only be corresponding to the future. That's the most important thing. Value is about the future, it's not about the past. That's very important. Okay? Any more questions? Okay, so those sorts of things you want to have in your mind. That's So in fact, in this particular case, essentially the wisdom of the crowds is wrong, right? Because they put F value, because come on, F must be the useful thing, but F is not, has no connection to MDT, because there is no single initial state where you start from. See, imagine if I ask this question in the exam instead of here. You know, it would have been so much more fun. I would have been done faster. He actually wound up spending like 10 full minutes talking about it. This is why I'm not getting far enough. Okay, we'll finish this. And then what I'm going to do are, so I'm going to start the attendance question, except I just leave it on for like several minutes, maybe like 10-15 minutes, and until I remember to take it out. But basically, list most of okay, I mean, I'm just basically getting some useful data out of this while I'm also getting you to do attendance. Okay, I'm going to start this, and I'm just going to leave this. Okay, and I'm going to just go forward. Okay. Anyway, I'll leave that there. So, we are going to continue talking about value and policy iteration for infinite horizon MDPs, which we got to last class already. Okay. So this is all reviewed. Infinite horizon MDP is basically you only have so you have only a power s policies, and then you basically can do value iteration just like you did value iteration for finite horizon MDP, except that there is no physical significance to the intermediate value functions until you reach the final value function. The final value function is the fixed point of this computation. That means if you apply one more iteration to this value function, it doesn't change. And it has to be that way. Otherwise, basically, you know, if there is a single value function, then essentially you should be able to reach by fixed points. And of course, there should be a proof. We'll talk about the proof in a minute. But that's how it works. And then we talked about this immediate problem. Why should value function converge at all? Given that, in fact, you know, the rewards can add up over an infinite horizon and they become infinitely large. And then we talked about this trick called discounting future reward with respect to current world. Okay, and so in particular, in a sense, rather than just add up the rewards that you get over a sequence, you multiply the reward you get at the t time step by, you know, beta power t. By the way, I keep saying gamma because for some reason I think in terms of gamma as the discount factor. This slide says beta, but that's, you know, beta, gamma, whichever, it's basically the discount factor. Okay, so the discount factor has to be 0 less than or equal to gamma less than or equal to 1. And if it's actually equal to 1, then in essence, it's not a discounted MDP at all. Okay. The advantage of doing this is that from your background in the geometric series, you know that even though the rewards are all different, if you assume that the maximum reward is Rmax, then you can basically show that if you have you know, beta power 0, R0, beta power 1, R1, beta power 2, R2, etc., and you can essentially divide and multiply by Rmax. Okay, if you do that, in essence, you know, it would become a normal power series, and you know that that power series has to be converging because it's in terms of beta power. You know, it's in terms of the common ratio is beta, which is less than 1. And so, in particular, whatever is the value of a state with respect to any policy would have to be bounded by this. would have to be bounded by this. It's not the actual value, but it will be bounded. This was our big worry because we were worried that the values might become infinity, and if they become infinity, then you get degenerate case. Okay, so that's what we looked at last class. And then we talked about some physical significance of the discount factor in terms of perpetual optimism here and perpetual pessimism here. In general, essentially, having a high enough beta assumes that you think the society will remain stable. Okay, that's one way of thinking about it. Okay, you are actually going to see the next day, in which case you will have like a high beta or high gamma. If you think this is it, then you're going to keep gamma to be low. Okay, so you're not looking too far into the future. In particular, actually, this is a worthwhile thing to understand. You can think of discount factor either as obviously this obvious interpretation, which is the amount by which future rewards are discounted with respect to the current rewards. So in essence, you're saying, I'm standing right now at the 0th time, and if I get the reward Rt at the tth time, that's really only worth beta power T Rt for me right now. Where beta is basically, of course, a number less than or equal to 1. So it's at most worth Rt, but oftentimes it can be much less. In fact, beta equal to 0, future reward is worth nothing right now for me. If it is closer to 0, future reward very quickly decays with respect to current. Okay, that's the obvious way you can think about it. But there is actually another very interesting way you can think about it. Theoretically, you can show that that's also a correct interpretation, which is you can think of the beta as the probability, as related to the probability that the MDP will be terminated at this stage. That means you will die. So basic idea is, as the agent is working, essentially with some probability 1 minus beta, the MDP will be terminated right now. Okay, if beta equal to 1, then with probability 0, sorry, it should be actually the probability, no, it should be, it's not 1 minus beta, it should be beta. It should be beta. So if beta equal to, no, it's correct. Yeah, so 1 minus beta. So if beta equal to 0, then with probability 1, you terminate. That's like saying there is no future. If beta equal to 0, so on the other hand, if beta equal to 0, if beta equal to 0, then with probability 1, you will be terminating. Beta equal to 1, with probability 0, you will be terminating. That means you will never be terminated. That's another nice way of thinking about it. How soon do you think you will die? We all think that we will. Really, the reality is, it's not like there is an actual horizon that you will live up to, right? I mean, it's not exactly a specific number. You kind of know that nobody seems to be living beyond 116, 127 or something. That's the maximum people seem to be living. But in theory, you could die much before that, and you may go all the way there. So in some sense, really the more interesting MDPs are quote unquote indefinite horizon Markov decision processes. Okay, there is finite horizon, infinite horizon, indefinite horizon. Your life is an indefinite horizon, right? And so in some sense, basically, this view actually helps you figure out that there is a, the higher the beta, the more you think you will live forever. Essentially. Okay, so that's a very useful view to keep in mind. Okay, so again, then basically, so there's a bunch of theory that we won't go into too much here, but we basically assume that optimal policy maximizes the value at each state. Optimal policies actually are guaranteed to exist. This is what Howard showed in 1960. He's a famous guy for that. And in fact, we can indeed restrict our attention to stationary policies, because as I pointed out last class, there could not be any non-stationary policies when you have infinite horizon, because you always have infinite amount of time to live. Okay, and then basically the V star, of course, is V pi for the optimal policy. Okay. Now there are two things that we'll talk about. One, of course, is given a policy, how do you compute the value? And the second is, how do you directly compute the value function, optimal value function? This is exactly what we did last time in finite horizon 2. But I'll again just repeat it, and so you shall sort of realize that we are doing pretty much the same thing that we did for finite horizon, except with this discount factor closure. Okay. The most important thing, of course, is if I give you a policy phi, then the value of that policy can be computed essentially by saying there is a set of simultaneous linear equations that you need to solve to get the values of all the states at the same time. Okay, so you imagine if suppose there are S states, then there are S variables, V pi S1, V pi S2, etc. up to V pi Sn, whatever the number of states you have. Okay, and you're trying to essentially connect the value of each of the state to value of its neighbors with respect to that policy. Basically in the finite horizon case too, you had equations like this, except those equations had a very specific structure where you get V0 first, then you can get V1 from V0, V2 from V1 and so on. Here you actually have to solve the real simultaneous equations in n variables. Do you remember solving simultaneous equations in n variables? What? In linear systems, yeah. Simultaneous linear equations, right? What do? Essentially, you do a matrix inversion. And there are many ways. You can do Gauss-Jordan elimination, you can do something else, etc. But essentially, computing the value of these states involves solving a set of linear equations. This looks as if, basically you realize this is a number, Rs, and then there's a beta, which is a real number, and then it's basically saying, given this policy, pi, then when you are in S, you consider all the neighbors that you can go to, with the probabilities you can go to those neighbors, multiplied by their values. But you don't know their values. Their values are connected to these guys' values, but you don't know any of their values. And you simultaneously solve for all of them at the same time. That's what simultaneous equations do for you. The good news is simultaneous equation solution is polynomial. You do realize this, right? I mean, you can solve n simultaneous equations in n variables in polynomial time. There can be special structure for these equations such that they can be solved in, essentially much less than polynomial time. Okay? The polynomial itself is across the board, but in general, if you have this diagonal structure, which is basically what happened in the finite horizon case, you could essentially solve. So the difference is between, imagine I said x plus y equal to 7, x minus y equal to 3, let's say, versus x plus y equal to 7, x equal to 3. Which would you rather solve? Which is easier to solve? Both are simultaneous linear equations, right? This one is also simultaneous linear equation. It's essentially just, you can plug all the way to nirvana. Whereas the other one you actually have to solve. Okay, that's pretty much what was happening between the finite horizon versus infinite horizon in terms of computing the value function. Okay, so how can you compute a value function of a policy? We are given not PR actually, which is the transition function, and then it's a simple linear system with n variables, and each variable is a value of a particular state, and then there are exactly n variables and exactly n constraints, and it's a linear system, so you can solve it. Okay, and you can do any number of things. One obvious one is essentially matrix inversion. You can do Gauss-Jordan, you can do any other. Okay. One cute thing, actually, to keep this in mind, one cute thing is, if you don't feel like solving the linear equation, okay, you could cut this equation and say it's an assignment. So, you start by initializing all the values to some random numbers. And then you use this assignment multiple times. So everybody looks around its neighbors and says, I reset my value based on my neighbor's values. And if everybody does that, it's a kind of a value iteration. It's not the full value iteration because there is no, as you will see in a minute, there is no max part there. And in fact, sometimes if you want to just partially evaluate a policy, which we will wind up doing when we do something called policy iteration, okay, then instead of solving these linear equations, you might decide to essentially act, you might decide to just apply some number of iterations of the value iteration. Okay, and then that will kind of improve the values to be closer to their final solution values. Just keep that in mind. Okay, now how about computing the optimal value function? Notice that the value function with respect to a single policy pi is linearly connected to its neighbors. The value function, the optimal value function V star essentially, which is among all the policies, there are only what? A power S policies, right? Among all these policies, there are some policies which are optimal. And for them, whatever their value is, that is V star. And what value iteration does is, rather than, even though what you are looking for is a policy, what value iteration does is it tries to compute the value function directly. And once you compute the optimal value function, you know what to do for policy. Okay, now how do you compute the optimal value function? This is the famous Bellman equation. Okay, you will keep hearing Bellman equation if you hang around long enough in AI, and you will keep hearing Bellman equation. His name, Richard Bellman is a pretty big guy. Okay, he's actually the guy who did this and essentially realized that in doing value iteration, you have this optimal substructure principle, and so he invented this notion of dynamic programming. Okay. Anyway, so V star S, that is the optimal value of a state S. There is no subscript anymore. There is no pi. It's V star S is going to be equal to R of S plus what you get from the neighbor's values. Previously, what you got from the neighbor's values is just the action you are supposed to do. For the action you are supposed to do, what is the expected value you get. But here you don't actually know which action you are supposed to do. Suppose you can do 10 different actions. For each action, you figure out this particular expected backed-up value. And then you take max over all the A's, max over all the actions. What is the best value you are getting at? This is exactly what you did in finite horizon 2. You're doing maxing over the actions. The only difference is now you multiply it by beta, because this is what you will get next step. And so it should be discounted by beta before being added to the current value R. The reward, immediate reward R. Okay? So if you do that, then you have just another set of equations. What's the difference between this and this? So you have these equations. You have these equations here, these equations here. The difference is this guy, max. These are not set of simultaneous, they are simultaneous equations, all right? But they are not simultaneous linear equations. Do you understand what I just said? They are actually simultaneous non-linear equations because of the max factor. Okay? And so you cannot directly use equation solving routines like the matrix inversion to solve this, because these are not linear equations. However, there are two ways you can do this. One will probably go over your head, other is what we will do in this class. One essentially is that you can actually solve this set of nonlinear equations by converting it into an equivalent linear program. How many of you have heard the word linear program? Okay, so linear programming essentially talks about optimizing some objective function. Let's say linear program talks about something like optimize 2x plus 3y plus 4z, okay, subject to constraints x minus 3y, maximize this, subject to the constraints, x minus 3y must be less than or equal to 7, x plus 3z minus 2, x plus 3z maybe, let's say, is greater than or equal to 4, and so on. A linear program is maximizing a linear objective function subject to a list of linear inequalities. And those of you who went to high school here and say we never heard of linear programming are delusional. Because there was one time when you were in high school, you did something called finite mathematics. It came in general in most US curriculums. It comes after algebra and before calculus. And that finite mathematics you will wind up doing linear programs and simplex analysis. And you never used it, so you've forgotten about it. But it turns out that actually you can convert this particular nonlinear equation solving into a linear program. And the good news is there are linear programming solvers all over the place. Linear programming, despite you not being aware of its existence, it's a huge deal. In fact, all airlines and all these other places, when they are trying to do resource scheduling, resource assignment, they essentially write, United basically says, I need to optimize my profit subject to this bunch of linear constraints, such as I only have these many, actual physical planes, I only have these many actual physical pilots, and I only have I have constraints like no pilot can, fly for more than 8 hours at a time or something. You have to take all these into consideration to come up with the best schedule for flights. And these are linear programs typically involving thousands of variables and thousands of constraints, and it's like a huge deal. Okay, and the good news, actually, one of the strange things is how this course connects everything to everything. Maybe it's just me, but it's also this course. Let's see, where did I go? Yeah, is that one very big issue is the complexity of linear programming. We know linear equation solution is polynomial. It wasn't clear for the longest time whether linear programming is polynomial or exponential. One of the most well-known algorithms for linear programming is this idea called simplex algorithm, which is what you would have heard of when you did linear programming in your high school, where in essence all these constraints essentially basically define hyperplanes in this high-dimensional space. And so you get like a polytope. If in 2 dimensions you get a polygon. And then the optimum solution would be at one of the corners of these polygons, this polygon. And simplex algorithm goes from corner to corner to corner to corner. And that's like the most optimal algorithm and the most efficient algorithm that somebody come up with. And it turns out that simplex algorithm is actually exponential complexity. So for the longest time, people didn't know whether linear programming is in class P